a small subspace, and I use elements from the subspace to produce noise and add to the system. So that's the basic idea. Okay? Okay, so this is what we'll do. And we'll use this guy to produce noise. How do you do that? Okay, very simple. So if you look at this map, look at this chart, the left-hand side is the original Matsumoto Imai system. If you only look on the left-hand side. And what we suggest is you have Z1 to ZR. These are perturbation agents for a small dimensional space. And you use them to produce quadratic functions, F1 to Fn, which are decided by Zi's. And then these guys produce some noise, and you just combine these two systems together. And that's just it. That's the idea. Okay? That's the very idea. And here, how do we control the size? We control size by R, which means we do not want R to be what? Too large. We want R to be small relative to the size of N. Okay? So this is the idea. Okay? So here, that's the mathematical details. So you have the original map. You just add the F1 to Fn from those space of a small dimension. Okay? So that's the basic idea, the construction. Okay? Okay? And those Fi's, I call the noise. It is a noise you add to the system. Okay? And then, so I define something called perturbation set. These are something which we'll use later to do decryption. Okay? And this is a set of size q to the r elements. Okay? Later we use it for decryption purpose. Okay? And then, so the most important thing I want to emphasize is this r is called the perturbation dimension, which decides the size of the scale of the noise you add to the system. Okay? So let's now see what is the Publickey. The Publickey is the same. The Publickey is just the new what? Polynomials you produce, new quadratic polynomial you produce. It's the same. But the secret key, and so encryption is the same. You just plug in the values and calculate the value of the polynomial. Okay? The interesting part is the private key. The private key consists of an original map F and consists of this Z1 to ZR, which means the subspace you defined, and this points in P, which is the perturbation set. And of course, the two map L1 and L2. And in the process of the decryption, you have to do a search. Okay? You have to do a search. And the search size is q to the r. Okay? You have to do a q to the r size search. Okay? One by one. Okay? And then you can use the original Matsumoto Imai map to find the preimage, which means find the plain text. And here you can see that's why r must be small, because the search size is q to the r. If r is large, of course, the system will be what? Very slow. Okay? So this is the basic idea of this construction. Okay? And then, of course, once you build a new system, you always ask, what is what? Security of the system. How secure it is. Okay? And before the beginning of this year, we do not know any effective way to attack it. Okay? As I mentioned earlier, the only general way to attack a multivariable system is to use something called a global basis. And global bases are general methods of solving polynomial equations. Okay? So we did some work to check how effectively global basis attack could be used to attack the perturbed cryptosystems. Okay? And in this case, we know there's global basis, also you have XL method. Unfortunately, in last year, in Asia Group 2004, there's work done by two research groups, one in France, one in Japan. They showed that the new global basis method proposed by Forget is much more efficient than XL. Therefore, the only thing we have to worry about is global basis. So in order to answer the question, we decide to systematically analyze what is going on for this case. Okay? And you can see, for our case, the system is defined more or less by two parameters. One is n, one is r. N is the original size, r is the perturbation dimension. You want to know what is the best choice of r, which means how much noise you should add such that the system is secure. Okay? And the interesting here is you realize if r equals 0, which is the original Matsumoto Imai case, we know the complexity is polynomial. But if r equal to n, which means the polynomial, I just randomly chose a polynomial. Therefore, in this case, the complexity is what? Exponential. So you have an evolution from what? In this case, very interesting. You have an evolution from polynomial to what? To exponential. And what you intend to find out is where this transition point happens, which means when the complexity starts to change from what? Polynomial to what? Exponential. Okay, so that's what we call the phase transition point. Another point we want to find out where's the saturation point, which means it turns out in terms of experiment we find out as you increase R, but up to a certain stage, even you increase R, the complexity will stay as the same. And this is the case, the whole system is saturated in terms of by the noise already. You don't need to add more noise. Okay? So this is the two things we're interested in finding out. And what we did is we used computer experiments. Okay? And the experiment is based on the F4 implementation, which is the fast global basis implementation down in Magma in Australia. We use their algorithm. Okay? And we did experiment, we time it, and also we recorded the memory, and then we discarded the bad data, which means because it turns out what happens here is that memory often is a problem. It's not the computing complexity. Often the program fails because we don't have enough memory. Okay? So if memory has problems, then the data is not reliable. Therefore, we delete all those points. So we derive enough data, and then we do the analysis of data. And what we found out, the interesting thing is that it seems to us when R less than 6, it's not good. If R less than 6, it stays as a polynomial. And somehow when R equal to 6, the system behaves as if it's exponential. Okay? And for the R equal to 6 case, we found out the attack complexity is more or less given by this function, which is 2 to the 11.4 times 2 to the 1.16n. This is the attack complexity. From this, we realize the conclusion is that for practical use, if you want to set up the security level to be 2 to the 80 triple DS, then you want to choose R equals 6, N equal to 100, which means you can build a system such that the block length is just 100 bits. Okay? So this is the example we will suggest for internal probation of mass model EMI system. However, there appeared new attacks against our system just at the beginning of this year. Okay? And the new method was developed by Professor Jacques Stern and his research group at École Supérieure in Paris. Okay? And what they did is something very interesting. They proposed differential analysis attack. Okay? So they pick up the perturbed mass model EMI system. Okay? They analyze the differential of this system. Okay? And observation is very interesting. What they did something very interesting. Okay? They observed that if you look at differential, if you can derive a linear map, the dimension, if you treat it as a linear map, the dimension of the kernel is fixed if the noise does not do anything. If the noise does anything, then the dimension of the kernel will change. Okay? They did a computer experiment. That's what they found out. Okay? Okay, that's what we found out. And then because of that observation, what they say is that let's find out who is noise, who is not noise. And then I can denoise it. Then I can break the system. Okay? And the fundamental weakness of the original perturbed mass model EMI you realize is because the difference, if you study differentials, and if you study linear map related to differentials, the dimension of the kernel is fixed. It does not change. It stays all the time. In some way, you should understand is you have a system such that in the background it's very pure. There's no noise There's no noise at all. And if you add noise, somehow they can They can use the fact that there's no noise in the background, they can tell who is the noise. Okay? So once they know that, they realize they can denoise it. Okay? And they can break the system. Okay? Which means they develop a way to To attack the perturbed mass model EMI system. Okay? Using differential analysis attack. Okay? And actually, we did a very similar work independently, but we were definitely after them. Okay? And their paper actually was just accepted in Asia Crypt 2005. Okay? It will be presented this year in May in Aarhus in Denmark. Okay? And this sounds very bad news to us. But actually, it is not that bad. Okay?